Okay, so I just want to remind you that everything we're doing in these first 2-3 weeks is very, very carefully chosen. So for your success in the middle of the course. So that means two things. If you're struggling, you need to get help quick. And that means another thing, that when you work on it, don't have a mindset of, I'm just going to get the homework done and move on. You've got to think about, you're learning this to retain it. So when it becomes just part of the harder stuff that we're doing, you won't stumble over this stuff, okay? So you really got to have a mindset when you're working on it is, I'm going to learn it for good. I'm going to retain it. So I can, later in the semester, I can draw from it and know what I'm doing, rather than just, I got the homework done, turn it in, move on, forget it. That's just going to kill you when we get into the middle. So we're choosing all this material very strategically and deliberately for what you need when we get to the calculus. Okay, so let's review some relative size stuff. Again, this is important. So estimate the relative size of A to B. Tell your neighbor, go. Estimate the relative size of A to B. So we're saying, how big is A measured in the standard of B? How much is A measured by the standard of B? What is it about? Okay, you should have said 0.8, 4/5, 3/4, 5/6, 0.8. Measuring A in the standard of B. Okay, so now I'm going to tell you that this is actually 18 and 23, so now I want an exact representation. Can you represent exactly what the relative size of A is to B? Tell your neighbor. Go. So what do we do mathematically to get relative size? That's what I'm asking here. What operation do you do?
Division.
A relative side. Okay, I heard division and multiplication. Is it a product or a quotient? Relative size. Quotient. So you should have said 18/23. That's precisely the size of A relative to B. That's the precise size of A relative to B.
I mean, isn't it as
Okay.
much 0.8 as much as the
want a
1
decimal?
Okay, what's that?
Isn't it as much 0.8 as much as the quantity would be?
Right. I guess.
That's what I said.
No, but how do we get the relative size? What is the relative size? It's a quotient, right? Okay, so let's review this. Why divide? How is it that 18/23 gives us that relative size? Do you remember? What are we saying? 18 over 23, or 18/23. Remember this process that we went through to show why division is what we need to do this? Yeah.
The first part with the relative size, you found the quantity of A in like quantity B.
Yeah.
And then the 3 over the 4. So then again, you're the application.
So, but what's the mechanics of 18 divided by 23 that measures the length of A? Yeah. Yeah, definitely. But like, what are the nuts and bolts of this 18 over 23? Right, that's the general idea. Now I'm getting into the nitty gritty. What are the nuts and bolts? Why divide 18 by 23? Yeah. No. Where does that come from? 18/23. 18/23.
So if you have quantity B into individual units,
Right.
it would be 23 units.
23 units in B.
A only has 18 plus 23.
Exactly. Did you hear what he said? If you break up quantity B into 23 units, you get 20/3. 20/3 of quantity B. And how many 20/3 of B make up A? 18. All right. So 18 of those 1/23 of B make up A. 18 of the 1/23 of B make up A. So that's why you divide. 18 divided by 23. And that's actually a better approximation is 0.783. Okay, 0.783. Okay, suppose this relative size is maintained as quantity B changes. How could you get the value of A for any given value of B? How could you get the value of A for any given value of B? Somebody knew, yeah. 0.783 times the value of B. That's what she wants. Yeah, this is exactly what relative size means. If A is 18/23 of B, and you have B, then you're going to take 18/23 of it, right? And how do you do that? What do you do to take 18/23 of something? You multiply, right? You're going to take 18/23 of the value of B to get the value of A. It's like two sides of the same coin, relative size and what is this principle here that we have? Is it scaling factor or constant multiple? Scaling factor or constant multiple reasoning? I'm hearing both. What do you think? Why constant multiple?
Because we're using factor 18 over 22
Okay.
to multiply whatever increase we find out.
All right, the whole point of constant multiple is that you're going to start with the value of one quantity and you're going to get the corresponding value of a different quantity. So we have value of B. We're going to multiply, and it's going to give us the associated value of a different quantity. That's constant multiple. Scaling is when you just have the same quantity resized. You multiply, and it resizes the same quantity, either larger or smaller. But if you're getting this corresponding value or associated value of a different quantity by multiplying, that's constant multiple. Okay, more practice. Go. Estimate the size of A relative to B. A relative to B.
It's a little more than 2. Yeah.
A little more than 2. A little more than 2. So 2 1/4, 2.1, 2.2, 2.3. That's ballpark, okay? An exact representation. Go. An exact representation of the size of A relative to B.
Easy. 35 over 16.
Okay? 35 over 16 will give us 2.19. So that's what the size of A is measured in the units of B, or relative to the size of B. Your relative size is quotient. Okay? Suppose this relative size is maintained as B changes, then what is the value of A? How would you get the value of A?
35 over 16.
Okay, it's going to be 35/16 or 2.19 times the value of B. So if this is how large A is relative to B, and you know how big B is, then you're going to multiply by that amount, right? It just should make sense. If that's how big B is relative to size A, then take any value of B, multiply it by that, and it'll give you the size of A. Okay, scaling factor or constant multiple?
Constant multiple.
Still constant multiple. We're starting with one quantity, we get the corresponding value of another. One more try. Size of B relative to A. Relative size of B to A.
About 5 or 6. Something like that. B to A.
B to A.
So 5 or 6.
1/6. I said 1/6. B to A. Measuring B with A as the measuring stick. 1/6. Exact representation. 0.59 over 3.6. It's about 0.164. Okay, suppose this relative size is maintained as A changes. Okay, then what will the value of B be given the value of A? 0.164 times the value of A. The size of B relative to A is about 1/6, and you knew what A was, then you're going to take 1/6 of it to get B. And to get 1/6 of it, you multiply. You multiply by 1/6. Should make sense. Okay, now I want to notice something. What do you notice about the value of the relative size and the value of the constant multiple?
Ratio between the two is always the same.
Right, so the ratio, or this quotient that gives you the relative size, is the constant multiple, as long as you have these straight, right? So if you change, oh, what happened?
Maybe accidentally pushed a button.
But actually, this is something I've always wanted to do, is go back to this beginning of the same slide instantly. But that's not now. I didn't want to do it now. All right, let's try it again. Oh, maybe it's because this is off. Okay. Thank you for your patience. Okay, we're almost back here. Almost got it. Come on.
There we go.
Okay, so as long as, if it's the relative size of B to A, then as long as you have the value of A and you want the value of B, then that constant multiple is the same as the relative size. So the size of how big B is relative to A, with its magnitude, given the value of A, that's what you're going to multiply by to get the value of B. So they're the same. Right? So same value. As long as these are ordered correctly, right? You have to have the right one, the correct one there and the correct one there, okay? Okay, so let's talk about, let's see here. Okay, what's the relative size of quantity B with respect to quantity A?
Right on. 3 or 4. Something.
The size of B relative to A. Size of B relative to A.
Someone between 3 and 4.
Oh, 3 over.
3. It's close to 3.
What do you think? Size of B relative to A is?
Somewhere around 3.
Okay, let me give you some help.
High. It's
So this should help you see more precisely what is the size of B relative to A. So you should be saying 3. What would be an exact representation of that relative size besides the number 3? So given what I've given you here, how could you represent that relative size? What could you say?
3 over 1.
It's 3 times the quantity.
So we want to set what is the relative size as a quotient. Quotient of y over x. So when I say quantity B and quantity A and B aren't variables. All right, so let's point that out. A and B are like height, a height quantity, or time elapsed quantity, or a distance quantity, or a temperature quantity. Okay, and then the value of those, the value of the height or the value of the temperature, I'm showing as x and y. Those are variables that take on the values. Okay, so we'll use that notation. So just be aware of that. When you say quantity A or quantity B, So you would replace A or B with some characteristic, something that's measured. Okay? Like mass or weight or volume or time elapsed. And then the variables that take on the values of those quantities I'm showing here as x and y. And so that relative size could be represented as y over x, and it is 3. Okay? Y over x equals 3. Okay, so does y change with constant rate of change with respect to x? You did some little study on constant rate of change before today. Does it change with constant rate of change?
Yes.
And what is the value of the constant rate of change?
Delta.
What is the value of the constant rate of change of y with respect to x?
Delta y over delta.
Okay? Can you say what the number is? 3, right? Y is changing 3 times as fast as x. Is another way to say it. Y is increasing 3 times as fast as x is increasing, and that's staying constant. That's staying constant. The constant rate of change is 3. Okay, let's look at another one. How about this one? What's the size of y relative to b? Or sorry, size of quantity b relative to quantity a? Still about 3, right? Looks about 3. Okay, so what's different about this than the previous example? Okay, but talk about relative size. What if you're talking about relative size? What's going on here?
Relative size.
That's right. That's right. So the relative size is changing. It's not constant. So at first, when I showed it to you, that relative size was about 3, right? And then about here,
1.
what's the relative size now? You should be thinking 1. Relative size is 1. What about now? Relative size? About 3/4. Continually, so this relative size of quantity B to quantity A is changing. Y over X is not a constant value. Y divided by X is not a constant value. Okay, but could relative size have anything to do with this? So let me give you a different view of the exact same bars. Watch. Is there enough contrast there? Can you see the red versus the black?
Yep.
Let me try something here. That's better. I think this is it. Beautiful. Okay, that has more contrast. All right, so can we, now that I've shown you this view of it, what might I be showing by the turquoise or the light blue? What might I be showing by the light blue? It's the idea that I'm showing by the light blue parts of the bars. I'm hearing people say it. It's like we started at a certain value of x and y taken together, and then now we're looking at an amount of change, right? Amount of change. So, talk about relative size now. Can you talk about relative size now? We said y over x, that ratio changes. That ratio changes. The relative size of b to a is not maintained. So now I'm giving you something more to talk about. Go, relative size. What can you talk about here? Okay, let me help you even more. Watch this. Whoa. It's the same two bars the whole time. I just moved bar B back a little bit. Go. Talk.
Just about one half. Depends on how you look at it. If you want to need A and each change relative to A, if you want to look at it, it's just like the quiz.
Okay, what can we say about relative size? Is there anything new we can add to the conversation now about relative size? Is that a hand? You want to try? So what did you talk about? Now that I changed your perspective on these same two bars, increasing together, can you say something new about relative size? So what's twice as much as quantity? The change of x is twice as much. Okay, this is change in y. So what about the relative size? So what about the change in y? If we were going to measure the change in y in the units of the change in x, would the relative size be maintained? What is that relative size of the change in y with respect to the change in x? About a half, right? Okay, so let's go back to the original view of this. These are the same two quantities increasing together the exact same way, just the original view. Is y changing with a constant rate of change with respect to x? Is y changing with a constant rate of change with respect to x? Some nods. Yes or no? Some shakes.
The rate of change.
Y is changing, but you're saying y with respect to the constant rate of change of x.
Are these two quantities changing with constant rate of change? I heard both. All right, let's summarize here. Let's summarize. Let's go back and look at them both again. Okay, here we go. Here was the first one. Here was the first one that we looked at. Is the size of y2 relative to x maintained? Yes or no? Yes. Y over x is a constant. Is the size of delta y relative to delta x maintained? If the actual quantities have the relative size maintained, then certainly the changes will be maintained as well. Okay? K is 3. And so therefore y is increasing or increases 3 times as fast as x for all x. Would you buy that? K is 3. This ratio of y to x or delta y to delta x is 3. And so y is increasing 3 times as fast as x for all x. So question, does y change at a constant rate with respect to x? And the constant rate is 3. Okay? Easy, right? So now the second situation. Second situation, ready? Here we go. Here's the second situation I showed you. Is the size of y relative to x maintained? No. And then I showed you the exact same two quantities changing together. Exact same two changing quantities as they change together. Is the size of delta y to delta x maintained? Yes. And it's 1/2. It's 1/2. So going back to that, so in this original thing, any given change in y relative to the corresponding change in x is 1/2. So would you buy this? Y is increasing half as fast as x. Y increases half as fast as x because delta y over delta x is always 1/2.
Would buy it.
Buy it? True? Okay, so here's the $100,000 question. Is y changing at a constant rate with respect to x?
No.
Is y changing at a constant rate with respect to x? Who did their homework? What does it mean for two quantities to change with a constant rate of change? The ratio of the changes is constant. Yes. Yes. Yes, yes, yes.
Since the,
Yeah.
since the change increases y increases half as fast as x, this makes it prove to be constant.
What's that?
This makes it prove to be constant.
This is what makes the constant rate of change, right here. Okay. So if, looking at the quantities themselves, if that ratio of y to x is constant, then that's a given. You got constant rate of change. There's just no question, like that first example where y was always 3 times as great as x. Okay? But it's not necessary. What's necessary for constant rate of change is just that the changes maintain a constant ratio. Okay? So let me prove this to you. I want to prove this to you. Ready? Check this out. Here's that same second scenario right here. Same second scenario. Just a different format. Do you buy that? That's the same, basically the same thing as I showed you before, okay? And so the bottom bar is x, and then the top bar, the length of it is y. Okay, so just like we've done before, check this out. Just like we've done before, I'm going to take that y bar. Whoa. Oh my goodness. Boom. I'm going to put it there. And then what I'm going to do? Turn on the airplane, right? Turn on the airplane. Can you see it in the back? See the trail that's leaving? What's that trail that is leaving? Curved or straight? Straight. Is y changing at a constant rate with respect to x? Yes, you get a line. When you take those two quantities together, you get a line and so it's all about the ratio of the changes, not the ratio of the quantities themselves. Oh, I didn't want that. So if I look at a change in x here, maybe, try it again, I can do better. A change in x like this, corresponding change in y. Change in x here, oh my goodness. So I'm showing a change in x. Say x1. How could you write the corresponding change in y? Change in y1 would equal what? How could you write an expression that would give us that corresponding change in y? And what's k? What is it? 1/2. Okay? Delta x2. How would you get delta y2? 1/2.
Delta x
Still 1/2.
The relative size to the change in y, the relative size of the change in y to the change of x is always 1/2. So to get the corresponding change in y, you just multiply your given change in x by 1/2 and you get the corresponding. So it's that ratio of the changes holding constant that gives us a linear equation, gives us constant rate of change. Even though the ratio of y to x is it's always changing. The ratio of y to x is always changing, but the ratio of the changes is staying the same at 1/2. Okay. So let's summarize this. Constant rate of change. Let quantities a and b be represented by variables x and y. So x and y take on the numbers. A and b is like height, depth, temperature, distance, pressure, okay? If b varies at a constant rate of change with respect to a, that's synonymous with, from your reading, do you remember what we were just talking about now? Does it have to do with x and y or something else? It has to do with delta x and delta y. Those have to be proportional. The changes in b are proportional to changes in a. Changes in b are proportional to changes in a. Delta y is proportional to delta x. And then there's two mathematical results of that. The first is that that ratio is constant. That's proportionality, right? Proportionality, your ratio is constant. And then the other important result is that if you knew delta x, you multiply it by k and you get delta y. What perspective on multiplication is this? What perspective on multiplication is this? Scaling, constant multiple. Constant multiple. We have delta x multiplying by k, the constant multiple, gives us the corresponding delta y. So that's why we emphasize that, because this is our constant multiple reasoning for multiplication. This is relative size. Relative size. A quotient is relative size. Okay, so this says the size of delta y relative to delta x is constant. And this one says that the change in y is a constant multiple of the change in x. Okay, so for this one, what's the value of k? What's the value of k? This was the second example we saw. It's the same thing, 0.5, okay? It's the same, remember, and we talked earlier in class, the relative size is the constant multiple. The relative size is the constant multiple. In this case, for this example, 1/2, or 0.5. Okay, then the first example. What's the relative size of delta y to delta x? 3. What's the constant multiple times delta x that gives delta y? 3.
Still 3.
Okay?
Professor,
Yes, sir.
does the first one be considered a scaling reasoning? Is that actually
No, because it's quotient. No, scaling. So scaling versus constant multiple. Those are perspectives on multiplication, and this is quotient. This is division. So it's relative size. Okay, so let's practice. We'll leave this up here, just so, because these are the two main mathematical results or main mathematical constructs of constant rate of change. So we're going to get some examples going here. Okay, so you're buying a certain trail mix that costs $2.75 per pound. What does that mean? That means the cost in dollars is always 2.75 times the number of pounds that you buy. Isn't that true? The cost it'll cost you is always 2.7 times the number of pounds that you buy. So that should feel very much like what we're doing. So define each variable. So here, this is students who succeed. This is what they can do well. They can take a situation and they can attend to the quantities and they can define variables well. So we're going to practice. In this situation, what is x? What is y? What is delta x? What is delta y? And what is k? You can talk amongst yourselves. Work them out. Super important. Write it out. Practice writing it out. Okay? Write them out. Okay, so for x, to say just x is pounds or x is trail mix is not going to cut it. Okay, so you've got to be specific and include your units. The number of pounds of mix. So something that specific, and it has to have with pounds in it. So, or the weight of the trail mix in pounds. That would be fine. The weight of trail mix in pounds that you buy. What is y? The cost of x pounds, right? The cost of, in pounds, of x pounds, in dollars, right? So the cost of your trail mix in dollars. So what would delta x be? Change in weight in pounds, or the change in the number of pounds. You can say the change in weight in pounds, or the change in the number of pounds. Delta y? Change in the cost in dollars. How much the cost changes for a given change in pounds. And what is K? Okay, so more than just, yeah, so it's the delta y over delta x, but in this scenario, how would you define what K is? So that I didn't do great there. The constant rate of change of pounds with respect to, or cost with respect to pounds. So this is dollars per pound. I need to. So what I had originally wasn't great. This is better. The constant rate of change of cost with respect to weight, which is $2.7 per pound. $2.75 per pound. Okay, so when you're working with real-world situations, which we will all semester, students who identify the quantities and are always attending and keeping track of the quantities as they're solving are the ones who succeed. It's just bottom line. That's all there is to it. If you're just trying to remember a procedure, I put this number here, I plug in here, I crank out an answer, you're going to get lost. We're taking the time to do this because this will be a crucial skill all semester long. Okay. So write an expression using 3 variables that computes the constant rate of change. So what expression would actually compute the value of K, the constant rate of change? What would it be? So we're doing this and we want to get a value for the constant rate. How would we set up an expression that would do that? Delta y over delta x. Delta y over delta x. Okay?
Yeah.
Write an expression that computes the change in cost given the change in number of pounds. So you have the number of pounds that you change, and you want to know your change in cost. Write an expression that would do that. Write an expression that would do that. I'm going to call on someone here. This is not trivial. We know the change in the weight, and we want to know the change in cost. So what equation, expression would do that? Michael, can you do that? Tell me. Okay, so that's the previous question that would compute. So change in y over change in x. That's the previous question. If we wanted to compute the constant rate of change. This is a slightly different situation. Now I have a change in weight, and I want to know the change in cost. That's what it is. So what that question is asking right there is exactly this. You know the change in weight, and you want the associated change in cost. Right? This is constant multiple reasoning. We know the value of one quantity. We're going to use multiplication to get the associated value of the other. So, change in weight times our 2.75 is going to give the corresponding change in cost. Make sense? Okay. After scooping some mix into your bag, you decide you want to buy more. The additional cost you will pay for 1.5 more pounds of trail mix is 2.75 times $1.5. Go. What is delta x? What is delta y? What is k? In this specific scenario.
You could actually
Okay, how about with the red pen? Tell me. So what's delta x in this situation? Okay, and what is it? She wants 1.5 pounds. Is that right?
That is right.
What's delta y?
Yep.
Right, k, so delta y equals k delta x. Delta y is k delta x, and the units is dollars. And what's k? 2.75.
Okay, will always be the same.
Taking written words and applying our symbols or notation to start modeling it with mathematics. That's what we're working on. You've got the written words. We're learning to model with variables and expressions. Okay. Next, you remove 0.4 pounds from your bag and return it to the bin when no one's looking. Right? Go. What is delta x, delta y, and k? Taking away, yeah, so what would your change be if you take away 0.4? Negative. Let's hear what we think. Okay, right here, the blue shirt. Yeah, no, you. No. Batman. All right, he wants negative 0.4 for delta x. Negative? Yes. The weight is going down. It's a decreasing quantity. It's got to be negative. So if you did final minus initial, what the final would be less than the initial, and when you do that subtraction, you'll get a negative value, and so that negative tells us the amount is going down. Okay, keep going.
Negative 0.4 times 2.75.
Okay, and he wants. Can I just switch the order?
Yep.
So our 2.75 times. Does anyone? And what is that? What kind of number does that give us?
Negative number.
Negative. So doesn't make sense that that's negative. So it's dollars. We're going to get some number. It's going to be less. It's going to be a negative also.
You'll get money back.
So what happened to your cost? It went down as well. So it's change. The value of its change is also negative. Okay. So if the pounds goes down, negative change. The cost goes down, negative change. K, is it negative?
Negative.
K is not.
It's not. K is still positive. Pounds, dollars per pound.
Still 2.75.
Okay, new situation. Here we go. Soldier lowers an American flag from top of pole at 0.75 meters per second, meaning that in any period of time, the number of meters that the flag descends is 0.7 times the number of seconds in that period of time. Okay? So if it's descending at 0.75 meters per second, that means that in any period of time, the number of meters, look, in any period of time, the numbers of meters that it descends is 0.75 times that amount of time. See that? That's what that means. Okay, so now I want you to define variables, but one of the variables has to be the height of the flag from the ground. The height of the flag from the ground has to be one of your variables. You have to decide which one. But don't do the distance the flag has traveled from the top. I want the height of the flag from the ground. Okay? Go. One of those has to be the height of the flag from the ground. Write them out. Write them out. Practice.
X is time in seconds. What would K be? But it'd be changing.
So there is a right answer here. You have to have these right. There is a correct answer for all of them. Okay, so there's no, you don't have a choice here. With this restriction. That restriction, the height of the flag has to be one of them. Those all have a right answer. Okay, so will that work then with just being hit up there? Check it, right? So see if that will make sense. So you took delta y by
Tell me
So on this one, it helps start with K. Start with K. And then decide what your x and y is based on our constant rate of change, the map. What is k here?
175 meters per second.
Okay, got to be careful. Y is height. So you got to be on top of this. There's something different here. All right, so let's hear from somebody. How about all the way in back? Eric, how'd you do? What did you think the x was?
X is just seconds.
Seconds. What seconds? Okay, so number of seconds since the flag left the top. So we need a reference starting time. Whenever you define a time quantity, you got to make sure you have that starting time, that reference time. So this is since the flag left the top. Okay, then what is y? Height of the flag in meters. To the word, right? Height of the flag in meters. Okay, so delta x is? Change in time in seconds. Delta y? Change in the flag's height in meters. So here's, did we get this? What is k? 0.75. Is it 0.75?
Negative 0.75.
Oh, he's saying negative. Is it negative or positive? It's negative. Negative 0.75. Why? Because when x goes up, y goes down. When the time increases, the height is decreasing. So for a positive change in x, you're going to have a negative change in y, which will give us a negative ratio. Does it make sense? Okay. Here's an example where y over x is not constant. Y over x, the height divided by the time that's gone by is not constant because x is increasing and y is decreasing. There's no way that that ratio could be constant. But do we have constant rate of change?
Yes.
Y and x are in constant rate of change because it's about the changes. It's about the ratio of the changes, which is always negative 0.75. Okay. Write an expression that computes the constant rate of change. So what expression would compute the value of k? If you needed to compute the value of k, what would you do? You should be thinking this. Right here. That's it. That computes the constant rate of change. You take a delta y divided by a corresponding delta x. Next. Write an expression that computes the change in height for any given change in time. So you know a change in time, and you want to compute the change in height. What expression would you have? What expression would you have? Have it right here. Yeah. You said delta y equals k, which is, we can do negative 0.75 times. Does that mathematical statement match this English statement? Are those a match? Yeah. You know the change in time. This will crank out the change in height. Okay, so this is a crucial ability that you take English words and you can model it with these symbols, right? So we can then do the mathematics. Okay, how much does the height change from 4 seconds to 7.2 seconds since the flag top left the top of the pole? What is? Go. Go. Okay, what's the change in x?
3.2.
3.2. Final value of x minus initial value of x. So this is the general idea. X final minus x initial. So 7.2 minus 4 is 3.2 seconds. Delta y then is any change in y is the constant multiple times the change in x. And our constant multiple is times delta x, which is 3.2. K is negative 0.75. Okay, so I've told you this before, but it's huge. This may feel easy, you got it, 95% or 100%, you got it, but it's going to fade. You have to reinforce this, learn it, retain it, because it's going to come up all semester. We have to know this stuff, all semester long.
All the way to the very end.
Have a great Tuesday.